So previously we have discussed many things about knife set theory, and today topic of our discussion is function. So what is function, or what is the motivation behind studying function? Actually, different kind of functions occur whenever we study mathematics, different evening of mathematics, or many in many other subjects, in a great variety of situations. So here we shall need the full power of the general concept of a function, and since its modern meaning is much broader and deeper than its elementary meaning, we discuss this concept in considerable details and develop its main abstract properties. So let us begin with a brief inspection of some simple examples. So we can consider an elementary function, for example, y equals to x square. Okay, so x is the real variable. So what do you have in mind when you call this is a function and say that y is a function of x? In a nutshell, we are drawing attention to the fact that each real number x has linked to it a specific real number y, which can be calculated according to a rule, or you can say a law of correspondence, that rule given by the formula. So we have here a process which, applied to any real number x, it does something to it. Here it's squaring it, and then it produces another real number y. What is y? The square of x. So you can take another example. So if you can take y equals to x cubed minus 3x, or you can take y equals to x square plus 1 to the power minus 1, or inverse. These are two examples, simple examples of function of real variable x, and each is given by a rule in the form of an algebraic expression. This algebraic expression specifies the exact manner in which the value of y depends on the value of x. The rules for the function we have just mentioned are expressed by formulas. In general, this is possible only for functions of a very simple kind, or for those which are sufficiently important to deserve special symbol of their own. So consider, for instance, the function of all real variable x defined as follows. For each real number x, write x as an infinite decimal. How? Using the scheme of decimal expansion, in which infinite chains of nines are avoided, in which, for example, 1/4 is represented by 0.250000 this way, rather than by just 0.249999 this way. Then let y be the 59th digit after the decimal point. Let y be the 59th digit after the decimal point. There is, of course, no standard formula for this function, but nevertheless is a perfectly representable, or not representable but respectable function, whose rule is given by a verbal description. On the other hand, you can take the function y equals to sine x of the real variable x. It is so important that its rule, though fully as complicated as the one just defined, is assigned the special symbol SIN. So when discussing functions in general, we want to allow for all sort of rules and to talk about them all at once. So we usually employ non-committal notations like y equals to fx or y equals to gx, so on. So each of the functions mentioned above is defined for all real numbers x. The example y equals to 1 by x shows that this restriction is much too severe, or this function is defined only for non-zero values of x. Similarly, y equals to log x. You can take y equals to log x. It is defined only for positive values of x. And if you take y equals to sine inverse x, then it is defined only for values of x which lie in the interval -1 to +1, both included. So whatever our conception of a function may be, it should certainly be broad enough to include examples like this, which are defined only for some values of the real variable x. In real analysis, the notion of function is introduced in the following way. So we are going through the formal definition. So let x be any non-empty set of real numbers. X be any non-empty set of real numbers. We say that a function y equals to f of x is defined on x if the rule f associates a definite real number small y with each real number small x in capital X. Okay. So I am repeating the definition again. Let x be any non-empty set of real numbers. We say that a function y equals to fx is defined on x if the rule f associates a definite real number y with each real number x in capital X. The specific nature of the rule f is totally irrelevant to the concept of a function. The set capital X is called the domain of the given function, and the set y of all the values it assumes is called its range. If we speak of complex numbers here instead of real numbers, we have the notion of function. We do have the notion of functions as it is used in complex analysis. You will see in future. This point of view toward functions is actually a bit more general than is needed for the aim of our analysis, but it isn't nearly general enough for our purpose. Okay. The set x and y above were taken to be a set of numbers. If we now remove even this restriction and allow x and y to be completely arbitrary non-empty sets, then we arrive at the most inclusive concept of a function. Okay, so we remove the what we have taken, that is x and y a number set. From that we move on to any abstract set. Okay, so in this case we will get an inclusive concept of a function. By way of illustration, suppose that x is the set of all squares in a plane, and that capital Y is the set of all circles in the same plane. So x is the set of all squares in a plane, and capital Y is the set of all circles in the same plane. You can take it. We can define the function y equals to fx by requiring that the rule if associate with each square x in the circle we can define a function y equals to fx by requiring that the rule if associate with each square small x, that circle y, which is inscribed in it. Okay, so we associate with each square x that circle y which is inscribed in it. In general, there is no need at all for either x or y to be a set of numbers. All that is necessary, really necessary for us, for function, is two non-empty sets x and y and a rule. So a function consists of three objects. Number one, a non-empty set x. Number two, again another non-empty set y. And the third one, a rule which we call, or we could say, if, small f. And this rule should be meaningful and unambiguous in assigning to each element x in capital X a specific element y in capital Y. Okay, we can check the figure 1a. Okay, so what we have said, that a function consists of three objects, two non-empty sets x and y. These non-empty sets may be equal, but in general they need not. And a rule f which assigns to each element x in X a single fully determined element y in capital Y. The y which corresponds in this way to a given x is usually written as f of x, and it is called the image of x under the rule f. So small y is called the image of x under the rule f, or the value of f at the element x. This notation is supposed to be suggestive of the idea that the rule f takes the element x and does something to it to produce the element y equals to f of x. The rule f is often called mapping or transformation, or you can say operator, to amplify this concept of it. We then think of f as mapping x to y, or transforming x into y, or operating on x to produce y. Okay, the set capital X is called the domain of the function, and the set of all f of x's for all x in capital X is called its range. A function whose range consists of just one element is called a constant function. So I am again repeating. The fact that the rule f is often called a mapping or transformation or operator. Okay, so we then think of f as mapping x to y, or transforming x into y, or operating on x to produce y. The set capital X is called the domain of the function. The set capital X is called the domain of the function, and the set of all f of x. That means for all x in X, we collect f of x. This set is called the range of the function f. A function whose range consists of just one element is called a constant function. So we often denote by f from x to y as a function with rule f, domain capital X, and range contained in y, capital Y. This notation is useful because the essential parts of this function are displayed in a manner which emphasized that it is a composite object. So we denote a function like f is a function from x to y. Okay. In the figure 1a and 1b also, we have shown the convenient way of picturing the function. In the figure 1a, capital X and capital Y are different sets, and on the right side, on the right figure 1b, the sets are equal, and in which case we usually refer to f as a mapping of x into itself, figure 1b. If it is clear from the context that the sets x and y are, or if there is no real need to specify them explicitly, it is common practice to identify the function f from x to y with the rule f, and to speak of f alone as if it were the function under consideration. So we may not mention the set x and y. It may be relevant from the context of the thing we are studying. Okay, so we may not always mention x and y, and we just say the rule f. It sometimes happens that two perfectly definite set x and y, capital X and capital Y, are under discussion, and a mapping of x into y arises which has no natural symbol attached to it. If there is no necessity to invent a symbol for this mapping, and if it is quite clear what the mapping is, it is often convenient to designate it by small x goes to small y. Okay. Accordingly, the function we can take y equals to x square, this function. This will be written as x goes to x square, or x goes to y. We can also write x goes to y, where y is understood to be the square of x. So now we come to the extension of a function. So what do we mean by extension, or how can we extend a known function to another function? We're going to describe this thing. So a function f, small f, is called an extension of a function g, small g, or in the reverse sense, you can call that g is a restriction of f. Okay. So anyway, a function f is called an extension of the function g if two conditions are satisfied. Number one, the domain of that function f should contain the domain of G. So the first condition is domain of f should contain the domain of G, and the second condition, f of x should be equals to g of x for each x in the domain of G. So f and g, this function should be equal for each x in the domain of G. So in this case, for the extension of function, if the function f satisfies these two criteria, then we say that the function f is called an extension of G. Okay. Most of the mathematical analysis, both classical and modern, deals with functions whose values are real number or maybe complex number. This is also true of those parts of topology which are concerned with the foundation of analysis. If the range of function consists of real numbers, we call it a real function. So what is a real function? If the range of function consists of real number, we call it a real function. Similarly, what is a complex function? If the range of the function consists of complex number only, we say that the function is a complex function. Obviously, every real function is also a complex function, because in the extended sense or in the true sense, we can see any real number as a complex number too. We are heavily emphasizing on, or we will rather emphasize heavily on the real and complex function throughout our work or throughout our study here and obviously afterwards. So now we will discuss about three types of function: into function, onto function, and one-to-one. So first we can consider a mapping f from x to y. When we call f a mapping of x into y, we mean to suggest by this that the elements f of x, as x varies over all the elements of capital X, this collection of all fx need not fill up capital Y. I am repeating again. A function f, the mapping f of capital X into capital Y. When you call a function f, or a function or mapping f a mapping of x into y, we mean to suggest by this that the elements f of x, as x varies over all the elements of the set capital X, not fill up the set capital Y. But if it definitely does happen that the range of f equals the set capital Y, or if we specifically want to assume this, then we call f a mapping of capital X onto capital Y. So we have discussed two things. Number one is into mapping, and number two is onto mapping. So what is into mapping, or x into y? That means the collection of all fx should not, or it did not cover the set capital Y. And if it does, then the mapping f is said to be onto mapping. Okay. two different elements in X always have different images under F, then we call F a one-to-one mapping of X into Y. Okay. So what is one-to-one mapping? By one-to-one mapping, we mean that if we take two different elements from the domain of the function f, then the image, the image of that two different element should be different. That means if x, in mathematical sense, if x not equals to y, fx should not be equals to f of y. So different element has different images. So in this case, we call f a one-to-one mapping of x into y, capital X into capital Y. So now we talk about inverse mapping. So we have a mapping. How to define the inverse of that mapping? How we can define? So let f is a function from capital X to capital Y, from the set capital X to set capital Y, and the function is both onto and one-to-one. Then we can define its inverse function f inverse, which is again a function from the set capital Y to set capital X, and we can define it as follows. For each y, small y, in the set capital Y, we find that unique element small x in X in the set capital X, such that f of x equals to y. We then define small x to be f of inverse y. So if f of x equals to y, we write x equals to f inverse of y. This equation x equals to f inverse y is the result of solving y equals to f of x for x in just the same way, like we take functions like y equals to log y, and we then again take the antilog and we say that y equals to e to the power x, like that. Okay. So if it is a one-to-one mapping of capital X onto capital Y, it will sometimes be convenient to subordinate the conception of f as a mapping sending x over y's, and to emphasize its role as a link between x and y. Each x has linked to it precisely one y, which is equals to f of x. And turning the situation around, each y has linked to it exactly one x, which is again equals to x equals to f inverse y, in this way. So when we focus our attention on this aspect of a mapping, which is one-to-one onto, we usually call it one-to-one correspondence. Thus, f is a one-to-one correspondence between x and y, and f inverse is again a one-to-one correspondence between y to x. So we have described the scenario in the figure 2. So you can easily see that we have two sets, capital X and capital Y. The function f takes an element x, small x, from capital X, and it takes it to small y in the set capital Y. So inverse function, what it does, it takes that y from the set capital Y and it takes it back to small x in the set capital X. So we have, at this moment, we have introduced the concept of into mapping, onto mapping. What do you mean? What do you mean by one-to-one mapping, and also inverse mapping? And now we are going to see some examples by which we describe the properties or describe the types of function we have introduced earlier. So consider some functions from n to n, that is, what is n? N is natural numbers. So the function f of j, basically we will define four types of function: f1, f2, f3, f4. That's why you are using the symbol j in the suffix. So fj is a function from n to n, from the set of all natural numbers to the set of all natural numbers. We are going to define four types of function. Number one, if the function f1, what is the definition? F1 n is equals to n square. F2 function, what is the definition? F2 of n equals to n plus 3. F3 function, its definition goes like this: F3 of n is equals to floor of root n. So we have introduced, used a notation, this like third race, but without the upper things are different. So the upper part different is called the floor function. This symbol is actually floor. You use for floor function. This floor function is nothing but it's like it is greatest integer less than or equals x. So if we take a number, real number, and we use such symbol, then the floor function gives the greatest integer which is less than or equals x. Okay. So another function f4 is defined in this way: when n is odd, f4 is n minus 1. When n is even, f4 of n is equals to n plus 1. So we have introduced four types of function: f1, f2, f3, and f4, and we will now check among four function which one is one-to-one or which one is onto. So if we see the first function, if one n equals to n square, it is one-to-one, but it is not onto. It is one-to-one, it can be readily checked, it's very easy, but it's not onto. Why it's not onto? Is also very simple. We can easily see that if we take a number 5, this number 5 has no pre-image, or there is no n such that f of n is equals to 5, so it's not onto. Again, we move on to the second example, the function f2, which is defined in plus 3. It's not onto, but it is one-to-one. So why it is not onto? It's not onto because again you can't find an n such that f of n is equals to 1, because the domain is natural number, and again the codomain is also natural number. It is impossible to find any n such that f of n equals to 1. And if we move on to the third one, the float function, float of root n, this function is obviously onto function, but this function is not one to one. Why? If we take 2, or if you take 1, then f3 of 2 is equal to f3 of 1 is 1. So because of this float function, the value of f3 of 2 is coming as 1, and f3 of 1 is again 1. So both values are equal, but obviously 2 is not equals to 1, hence the function is not 1 to 1. And if we consider the last function, it can be readily checked, or you can also verify it, that this function is both 1 to 1 and onto. So we have given example of 4 functions. So 2 of them are 1 to 1 but not onto. One function is not 1 to 1 but onto, and the last function we have given the example that which satisfies both 1 to 1 and onto. So now we move on and we give some example of function. If it's a function from R to R, and obviously R is the real number, the set of all real number, the function fx is defined as 2x plus 3. This function is both 1 to 1 and onto. You can really verify. So it takes input as x and it gives output as 2x plus 3. So what is its inverse function, or can we really say about it? Yes, we can say about it, because the function f is both 1 to 1 and onto. So of course f inverse exists. So it can be readily checked. It is very easy to see that f inverse of y, this should be y minus 3 by 2, because it takes x and gives output as 2x plus 3. So in some way it takes that 2x plus 3 and it should give us back that x. So the function f inverse y, it can be readily calculated that it should be y minus 3 by 2. It takes y and gives output as y minus 3 by 2. So this very easy example, or easy to verify. So, but this thing doesn't hold always. As we have discussed, that there are many situations where this inverse function can't be readily found out. We have given one example. Let us say the function f of x is equals to x plus 2 plus sin x. So we have f of x. If we say y equals to fx, then we have y equals to x by 2 plus sin x. Now, if we want to find that f inverse function, we have to express x in terms of y. We have y in terms of x, but we need x in terms of y, and you see that this task is not possible. There are no way you can express x as a function of y explicitly. Okay. So we have given examples of different types of functions. Some is 1 to 1, some is 1 to, and then we move on and give examples of functions and its inverse function, and we have shown how to calculate this inverse function, and we have also shown that there are functions which is on 1 1 and on 2, but inverse function. Or we can't really solve the inverse function because in this function you can't express x in terms of y. Now we consider an arbitrary mapping f from x to y. The mapping f, which sends each element of capital X over to an element of capital Y, induces some following two important set mappings. So if it's a function from x to y, it induces two type of set mapping. If capital A is a subset of the set capital X, then its image f of capital A is the subset of capital Y defined by this way: f of capital A is equals to the collection of all f of x such that x belongs to capital. Okay. And our first set mapping is that which sends each capital A over to its corresponding f of capital A. Similarly, if capital B is a subset of capital Y, then its inverse image, f inverse of capital B, is the subset of capital X defined like this: f inverse of capital B is the collection of all x such that f of x belongs to B. So we have defined two types of set, f of A and f inverse of B. And this second set mapping pulls each capital B back to its corresponding f inverse B. So it is often essential for us to know how these set mappings behave with respect to set inclusion and operations on sets. We develop most of their significant features in the following. We have just write down that some important properties. The main properties of the first set mapping. The first set mapping means that f of capital A is equals to f of x such that x belongs to A. For this type of set mapping, we have f of phi is equals to phi. So it maps any null set to the null set. F of x is a subset of y. That means if maps the set x into set y. Again, if a1 and a2 be two sets such that a1 is a subset of a2, then f of a1 should be f of a1 should be subset of f of a2. So if we have a1 and a2 two sets such that a1 is a subset of a2, then f of a1 should be subset of f of a2. Now, if we have union of some sets, that is, if f of union over all I, ai, it should be equals to union over all I, f of ai. And the third one, corresponding intersection, f of intersection over all I, ai, is subset of intersection over all I, f of ai. So we should convince ourselves of the truth of these statements. For instance, to prove one, we would have to prove first that f of union over all ai is a subset of union over I f of ai. And the second, that union over I f of ai is a subset of f of union over I ai. Okay, so both ways. We have to show the both ways. So we have taken the we have previously taught that if we have to show that two sets are equal, we have to show, or this thing is equivalent to showing that one is subset of another. So we have to prove both ways. A proof of the first of these set inclusions, this might run as follows. An element in if union over I ai is the image of some element in union over I ai. Therefore, it is the image of an element in some ai. Therefore, it is in some f of ai. And so finally, it is in union over I f of ai. The irregularities and gaps which you notice in the statement, it is the essential feature of set map. For example, the image of an intersection need not equal the intersection of the images, because two disjoint sets can easily have images which are not disjoint. Further, without special assumptions, nothing can be said about the relation f of a whole complement and f of a complement. So in this case, we can't say anything. We can't say anything about f of a complement. That there is no relation between f of a complement and f of a complement. Okay. Now the second set mapping, the second set of mapping is f inverse. The inverse mapping is much better here. Its properties are satisfyingly complete and can be stated as follows. Number one, f inverse I is again of I. F inverse y is should be x. Now, if v1 is a subset of v2, then f inverse v1 should be subset of f inverse v2. Now, f inverse of union bi should be union of f inverse by. Again, f inverse of intersection bi is equals to intersection f inverse bi. And the last one, f inverse of b complement is equals to f inverse of b whole complement. And you can verify this statement by yourself. So now we are going to talk about multiplication of mapping. So the task is, we have to map f and g. How we can multiply them and produce another function or another mapping, it is our main concern here. So we start by some examples and then discuss this multiplication thing in details. So say we have a function y equals to fx, which is defined like is equals to x square plus 1, and another mapping z, which is equals to zy is equals to sine of y. So these two functions can be put together to form a single function. So how? We can define z equals to gf of x, which is nothing but g of fx, which is again g of x square plus 1, and equals to sine of x square plus 1. One of the most important tools of calculus is actually the chain rule. It explains how to differentiate functions of this kind. This manner of multiplying functions together is of basic importance for us as well, and we formalize it in general as follows. So suppose we have two functions. F is a function from x to y, capital X to capital Y, and g is a function from y to z, capital Y to capital Z. These are any two mappings. We define the product of these two mappings is actually denoted by gf, is a mapping from capital X to capital Z, by gf of x is equals to g of fx. So in other words, an element small x in capital X is taken to be, or is taken by f to the function, sorry, the element f of x in y, then g maps this fx to g of fx in z. So I am again repeating, we have an element small x in capital X. The function small f takes into the element f of x in capital Y, and then the function g maps this f of x to g of f of x in z. In this figure 3, it is a picture of this process. We see we have three sets x, y, z. The function f takes an element of x to an element of y. The function g takes an element from y to an element of z. And the multiplication function is like the gf. It takes an element from x and maps it to an element of z, capital Z. In this fashion, if this function f takes small x from that set capital X to the element f of x in capital Y, and the function, if the function g takes this element f of x in capital Y to an element in z, which is nothing but g of fx, then the composite function or the multiplied function takes this small x from capital X to this element in the set capital Z, and this element is also can be written as gf of x. So we have gf of x is equals to g of f of x. Okay. We observe that the two mappings involved here are not entirely arbitrary. For the set y, capital Y, which contains the range of the first function. Okay, so we observe that the two mappings involved here are not entirely arbitrary, because we have purposely taken the set capital Y, which contains the range of the first and equals the domain of the second. So this set Y contains the range of the first and equals the domain of the second. More generally, the product of two mappings is meaningful whenever the range of the first is contained in the domain of the second. We have regarded F as the first mapping, G as the second mapping. And in forming their product GF, their symbols have gotten turned around. This is a rather unpleasant phenomenon for which we blame the occasional perversity of mathematical symbols. Perhaps it will help us to keep this straight in mind, that if we want to remember to read the product GF, we have to read it from right to left. First we have to apply F, then we have to apply G. So we give a brief review of the terminologies which we have introduced. The first thing is a function. We have a set A and another set B. The function is from A to B, and it takes an element small a from this capital A to an element small b in capital B. We say the set capital A is the domain of the function f. The set B is called the codomain. This element B is called the image of the small a, or image of the element A under F, and in the other way we can also say that A is the pre-image of B under F. The range is defined, range of F is defined like that, is collection of all B's such that there exist small a in the set A which are mapped by the function to an element, to the element B. So these are the basic terminologies which we have introduced with respect to functions. So we have given some examples of some weird function which we often encounter in mathematics. Particularly, we have given examples of three functions which you can always study these three functions at AJOY. These three are very interesting functions. The first one is a function which you can see that f of x is equals to x whenever x is rational, and it is equals to 0 whenever x is irrational. So the question, actually this is a very weird function. If you see its weirdness, if you are going to draw the graph of this function, so it's your task to draw the function, or if you can draw it really. Okay. The second one is Tupper's formula. It's always a nice thing because it's also a weird thing, because it produces a graph that shows the formula itself. So the graph is exactly the same as the function. In a certain interval, you can see that the graph is this function itself. We now move on to another weird function. This is Thomae's function. Is also very important function. You will encounter it many times in the coming lectures, or you will have encountered it otherwise. This function is defined like this: f of x is equals to 1 by q whenever x is equals to p by q. That means any rational number. or is whenever x is equals to 0 or any other irrational number, f of x is equals to 0. So it's again your task, you have to draw the graph of this function. Or can you really draw it? So you can check it yourself, or you can study it. These three types of functions is very interesting.